Now we just have been concerned in quite a complicated way with a spherical surface, and much in contrast, we will look at a simple cube this time. The whole exercise 10.2 number 4 is aimed at better understanding this famous Gaussian theorem of divergence, which we just encountered looking at the first Maxwell equation. Now, this time very far away from application, just a simple mathematical example where it's not so simple actually. If you remember this vector field which we have encountered before, it will be quite interesting, but not so complicated to calculate. It just takes time. So now let us assume that our new surface S is now the surface of a cube. In R3, as usual, it's bounded by 6 faces, where these are described with mathematically with the planes given here. And this is quite simple. So actually, these are the coordinate equations of these planes, which are x equals 0, y equals 0, z equals 0, and then correspondingly x equals 1, y equals 1, and z equals 1. Why is it? Well, look at the sketch. The first 3 of these are quite simple. They are the so-called fundamental areas of the coordinate system, or they called well, the main areas, whatever. So look here, if x equals 0, of course, it means that we find ourselves in the drawing plane, in the screen here. You see what I mean? Because the x coordinate points toward us. If it's 0, we are inside the drawing plane. So we are in the YZ plane. It means, look here, the backhand face of this cube, which is numbered in green here with number 1 in green color. This is our first face of our unit cube. By the way, it's a unit cube. It has, you see, an edge length of 1. So, and also, look at the blue one. This is the normal vector pointing outward of the cube, which means at the backhand face, it must point to the rear. Okay, so that's why it has to take on coordinates -1, 0, 0. It must point in the negative x direction. So that's what we are concerned about. Setting up all the radius vector functions for all these faces of our cube surface, because we have to calculate a flux integral in the end. Okay, the second one, as you see here, denoted in green color with number 2, will be the side face of this cube. It will be the xy. Of course, it's not the whole xz. I wanted to say the xz plane. It's not the whole plane, but it's well, as a section of it, which is bounded by coordinate values from 0 to 1, as well for x as for z. Okay, and the third one, look here again. This was number 1, number 2. The third one, z equals 0, of course, means that we are in the bottom area of this coordinate system, which is the xy plane. And therefore, this is the bottom face of our cube here. And the red ones, as you see, number 4, 5, 6, analogously, are parallel to the before mentioned faces. So that, look at face 1 again, which is the backhand face of the cube. We just move it to the front by a distance of 1, and then we get our face number 4, which is the front side, the front face of the cube. Also, number 5 will be the right-hand face, and number 6 will be the top face. So that's all. But now, setting up radius vector functions for all these faces goes as follows. Writing S for surface 1, okay? So this is X vector. I just give it an index, the numbering according to these faces here. So the X vector for the first phase expressed with variables u and v, which are Cartesian, but I name them to be u and v anyway, because we have been accommodated to do so, will be some starting vector, which I just take the zero vector, the null vector to be. Why? Because obviously this phase number 1, also number 2 and 3, contain the origin, right? Now the cube is constructed in a way, so in such a way that the origin is one of its corners. Okay, that's important, because the whole cube, it is not centered around the origin. Instead, the origin is one of its edges, and it extends to all the positive half axes or semi-axes, right? So the origin is okay to be used as a starting vector. Then I add variable u times direction vector 0, 0, 1 plus variable v times direction vector 0, 1, 0. Why am I doing so? Well, this one is a unit vector in z direction, while this one is a unit vector in y direction. And since we see that the backhand face of this cube extends to the right and to the top, this is what we have to do. We have to increase u, starting from 0, ending at 1. Also v may increase starting from 0, ending at 1. And if we do so simultaneously, we will reach any point on the backhand side of our cube. So that's clear. One little problem will be to now look here. You might ask yourselves, why did I use the z vector first and the y vector second? I could also have exchanged them. That's true. But I decided for this form. Now look here, I just put this together to get 0 for the x component, of course, because the premise has been that x equals 0 for the first phase. Well, and then the second component will be v, and the third component will be u. Now this has a very important reason to use this order. The reason is for us to get mathematically guaranteed that the normal vector, which I explained to you, pointing to the rear side, has a negative x component. It's important for the flux integral to work correctly that all the normal vectors point outside of the cube, outside of the surface. And that's what we what we achieve by construction. Now, try and follow me. How is the normal vector officially mathematically calculated? And that's what I had used in the previous exercise implicitly. Let's just look here. What do we have to do? We have to take the tangent vector corresponding to u, then the tangent vector corresponding to v. These two have to be combined using a cross or a vector product, and this will give us the correct normal vector. Now let's test this in the at the example of S3. Let's look at S3 here. So that's the bottom face of the cube. Well, I decided to set it up in this way, to be VU0 in this order. So what does it mean? It means the x coordinate increases from 0 to 1. The y coordinate increases from 0 to 1, but z is equal to 0 and it stays 0. That's clear because it's the bottom face, right? So now increasing u means I walk along the y-axis, which is from left to right. Increasing u means I walk, although this was u, increasing v, I walk along the x-axis, which is from back to front, and thereby walking along this whole face. That's fine. But now, mathematically, I get as a first tangent vector in, you could say, direction of u variable, I have to take the partial derivatives of this vector for u, okay, with respect to u. So the first component does not depend on u, so the partial derivative will be 0. The second is u, and now taking the partial derivative with respect to u, I get constantly 1, and 0 differentiated for u stays 0. Now that's our xu tangent vector. Look, the 0, 1, 0. Looking here, you see it points to the right. And that's what happens when I keep v to be constant and let u increase from 0 to 1. I'm walking to the right in this direction, okay, around this, along this face of the cube, this bottom face. And analogously, I get the second tangent vector, referring to v, by taking the partial v derivative, which is 1, 0, 0, as you see. And now taking the vector product, you remember first row going around means second times third, 1 times 0, minus vice versa. You remember the way of calculating the vector product. So I get 0. I get 0 again for the second component. And the third component, look, is first times second minus second times first, which gets me -1. And that's why, in the end, mathematically, the normal vector points downward, which is outside of the cube. And that's the way it works. So you have to be careful deciding which coordinate direction you are using. For the assignment between the coordinate variables x, y, z and these auxiliary variables u and v must be chosen carefully so that we get mathematically the correct sign. Also, it's nice to know that all these normal vectors are automatically unit vectors due to the fact that this is a very simple geometrical setting. So it means there is no special Jacobian factor needed for the integration, because these auxiliary variables uv are, you could say, they are sort of Cartesian coordinates. So there's no rescaling or anything inside here. So that's what we set up first. And then next time we will try and calculate this total flux integral as a surface integral over the vector field v. So this will be, well, it will take some time, but we'll make it soon.